It's loading for a second.
Looks like we're good. Good to see you,
Hello,
Johan.
we're live. So I'm Johan Rotz. Yep. Hi, Sky. This is Sky Nelson. You might have remembered him from a couple of years ago when I did a podcast, and then I didn't do much of anything for almost 2 years. Yeah. So, hi, Sky. Introduce yourself.
I will. I'm Sky Nelson Isaacs. I wrote a book called Living in Flow, The Science of Synchronicity and How Your Choices Shape Your World a couple years ago. And the impetus for that book is research that I've been doing for a long time, over a decade, on synchronicity. Synchronicity is an experience of coincidence that stands out in your mind and makes you go, oh, there's something bigger than me going on here. And I saw those experiences in my life happening and realized that they were kind of a connection point between the inner world of our own spiritual growth, whatever that looks like for each of us, and the outer world that is described by physics. And I have a background as a physicist. I got my bachelor's degree at UC Berkeley and my master's at San Francisco State in physics. So I take my own real interest in understanding space and time as a physicist to understanding how we experience specific things in space and time that are meaningful for us, that actually change the way we think or do things in our day as human beings, not just as some abstract, physical reality.
So I was looking at your book a little bit, and I noticed, and of course, the notion of the outer world reflecting the inner world, right?
Yeah.
That shows up in, actually, we actually discussed that in a completely different context in my last podcast the other day, which was kind of funny. That shows it ties into Hermetic philosophy. But the thing with this is this seems to imply a connection between consciousness and physics, right?
Yeah.
And usually that will be associated with the, so we say, Copenhagenist branch of interpretations, right?
Mm-hmm.
Now, what I found interesting, though, and I've been tinkering with this, is that on the other side of it, though, there are people who want to, exclude it. Actually becoming less now. It used to be like much more predominant, but I think as of a couple of years ago, they did another poll and they found that 22% of physicists now believed in it basically was a mainstream view now that consciousness causes collapse, according to the polls.
Yeah, well, I would say the majority of physicists probably decide not to even have an opinion because they want to stay focused.
It's too controversial.
Yeah, they want to stay focused on what the math says and what the experiments say, and we have not resolved the question of what that really means about consciousness, and so it just gets in the way for a lot of folks. Let me lay out.
That's really boring from a. Oh yeah. Oh, go ahead.
Well, so let me lay out.
The thought I was going to finish though.
Yeah. So I think there's a little delay here, so we're like stepping over each other.
Go ahead.
You're talking about Copenhagen, and in the Copenhagen interpretation of
quantum
mechanics,
the other branch of interpretation.
Yes, so there are lots of different branches of interpretation. All of them have this question as to what causes the change of state of a system from many possibilities, which you can see on the wall behind me over here. It's like a tree shape of all the different possible ways that an experiment can unfold. And what takes the world from that description, which we know to be accurate at some level, to the description we have right now of having a single conversation about a single topic, not branching into many possibilities. And that's called collapse of the wave function. And the real question is to how do you interpret that? We have no real understanding of what causes that process, or if it is even a physical process at all. And what we do know is that the choice of how one measures a system, in other words, what's called an operator, what operator we choose to apply to the system, affects what our outcome possibilities are. The outcome possibilities only comply with whatever the choice of measurement we make is, and those measurements can interfere with each other. One type of measurement can disrupt the possibility of a different type of measurement. And so we do know from experiments that are called Bell inequalities, that this has been done very extensively, that the way to describe it is that there's no local realism, which is to say that properties in themselves don't exist separate from the observation of those properties. In other words, if I'm going to measure the spin of a electron in a magnetic field, the property of spin doesn't have a actual value of up or down before I measure it, but when I measure it, it has one of those values. And we like to think of the physical world as something that's out there that really exists. And so the spin really exists, but I'm going to measure it and we'll see what I find. Just depends on what's really there. There is nothing actually really there. What's there is a branching tree of all these possibilities. And when we measure it,
And that
then
actually
one of
applies
those
to
becomes actual.
Well, it is there because I'm looking at it right now, but
The tree?
yeah, you're not looking at it. Yeah. Well, from your
Right.
frame, it's not there. From mine, it is there because I'm
Right.
seeing it through the screen.
And I see it on
Now-
my screen too because of the camera, and that counts.
Oh, that counts. That counts. Okay.
Yeah.
So, now this actually applies to people try to divide the quantum world from the classical world, but they can't really do that. One kind of phases into the other, right? And they've actually, I think, tested this with the they tried to have this thesis saying that the quantum and classical are separate, and that at some point quantum just disappears, only classical, and that's actually not true. They've called the Leggett-Garg inequalities. They tested macro realism. They showed that yes, they have very heavy things in superposition, and they gave an example of a 2-ton metal block over at LIGO, which they used to, they have to have very sensitive instruments to detect gravity waves. And so that will actually include things of the sensitivity of the very minute wave particle distribution of a 2-ton metal block, for example.
Mm-hmm.
And it was fascinating because that entire block, this is like basically something the size of a car, is in superposition. And it's, if you apply the physics, it's not there before you observe it. I mean, it's there in Hilbert space, and it loads up, and it has the exact same properties it did. So it's not like anything changes in your experience that would be. It's not going to quantum tunnel to the garage door.
I like that you're emphasizing the distinction between it's not that it's not there if it's in superposition. It's there, but it's not in a definite particular form or state.
Our notion that stuff is, I mean, people, I saw this in a debate a little like either earlier this year or late last year. And it came up in the debate that someone was arguing that, yes, the world isn't actually there when you look at it and when you don't look at it. And that sounds kind of crazy. And so the realization of this is that I think a better way to think about this is that the world is never there as in the way that we think of it naively and kind of our intuitions. Mm-hmm. That's just our perceptual interface. It's if you think about what you're actually seeing, those are just perceptions. And there is something that's generating the world as it is not the world that we see it as. If you go, to philosophy with the whole direct realism thing. Mm-hmm. Indirect realism is there's Kant kind of got into this with the whole phenomenal interface barrier, and then beyond that is the noumenon. And so all you're really seeing that is quote unquote tangible and solid is your own perceptions.
Yeah.
What's beyond your perceptions is an entirely different matter, and looks like quantum mechanics is saying it's some of that sounds a lot more like Leibniz's metaphysics than Democritus's.
Well, I couldn't comment on that. You can tell me more about that. I want to point out that I think what you're saying is really true, and quantum mechanics is a great pointer into that dilemma. That you brought up the classical world versus the quantum world, and one of the things that I've researched and thought about in my writing is why do we think that there's a classical world? What do we define as the classical world, and why do we have to distinguish that from the quantum world? Well, the classical world is what we're used to. It's a world that has real things going on that are definite and easy to interpret and understand, kind of what's presented to us. And in the quantum description of things, what we found is that instead of that, we have electrons that seem to be in two different possible states, and they're not actually in those states. They're in a superposition of possibilities until they get measured, and then they choose one or the other. That seems really different, right? Because my car is not in two different states, unless you really think that if you try and create this idea that there's a huge quantum superposition of the car in multiple possible states, but really it's sitting out there in my driveway, doing a definite thing. So it seems like there's this dilemma between what the quantum world tells us and what the classical world really is, what we experience in the world. But it's really important to recognize that in the quantum world,
as you get closer to Planck's constant.
Well, in the quantum world, we never actually experience a superposition. When we measure a electron or in a magnetic field, or light coming from another star, when we measure that thing, it goes from being in many possible states to being in one state. The act of measurement is what makes it take a definite form. And if you think about your physical life, everything you've ever interacted with that has a real physical form is something that you've measured. So I'm measuring the wall behind me by looking at my screen right now, and I'm measuring you by looking at you on the screen. We've never interacted with something that we haven't interacted with, and it's the interaction that makes it take a definite form. So the question I ask is, what would we really expect to see if quantum mechanics did apply to the macroscopic world? And I think we would see exactly the same thing we see now, a world that looks definite and formed.
There is an interesting thought about this of when you said that we've never actually seen a superposition. That is actually valid, because whenever you measure the wave function, it collapses and, so on. But there is so we say a external, you have this notion being this external world, right? The world is all external, and you're focused on this one half of the data, which is the empirical side of it. And there was a development since the last time we spoke that kind of makes this a little more interesting, and that ties into the outer world. Notice here, the outer world is the empirical, right? And you mentioned earlier on it corresponds to the inner world. Well, there is actually a hard scientific development recently that has come to light that is, I think we talked about it a little bit, but there's actually very solid evidence for it now that is kind of tying into the inner world. And that is, maybe we do actually experience these superposed states, but not in the empirical way that we think we do, not the empirical sense of it. And that is, are you familiar with Matthew Fisher's studies with rats and lithium isotopes?
No. Well, okay, no, so tell me more.
Okay, what they did is they realized, if you have if you think of the brain, kind of a materialistic thinking of this is just like a classical computer, and treat all the neurons classically, and it's just classical neurons firing, and that explains consciousness somehow, which doesn't explain, because from a philosophy of mind point of view, you have to bridge an explanatory gap, and there's no explanatory gap to be, they just treat it like the phenomenal side of it's not even there. Mm-hmm. However, what he did, he said, let's suppose that's true, and then we have, rats having lithium isotopes, right? Now, lithium, of course, is the third atom on the periodic table, and it has electrons. So it shouldn't matter if you're using lithium-6 or lithium-7, right? It's just the same chemical either way. It should have the same exact effect on the brain, right? Well, it turns out that that's not true. You'd think that would be true, but it's not true. And he actually was going to propose this experiment be done, but then he discovered that someone actually had already done it back in 1984, which is the year I was born, which is kind of cool. But basically what happened is the rats that were given lithium-7, rats having lithium. Hi, GM. He was on my podcast before. So Lewis R was too. So anyway, basically the rats that had the lithium-7 became much more had much stronger maternal instincts than the ones that had no lithium-6. Mm-hmm. And this is like very marked behavior. They had a whole study done, and the thing with it is this is they weren't testing for this explicitly in the experiment. They did this test as well in the experiment because it was kind of indirectly related. And Fisher was kind of commenting on how extraordinary this was, and yet in the study they just treated it as this kind of thing, and they didn't really comment on it much. It's just like, oh, by the way, we did this extra lithium isotope study, and oh, this is kind of interesting. And he looks at the data back, again, digs his data up from this paper, and he's like, whoa, look at this. There's very strong differences in cognitive behavior in the rats that had the lithium-7 and the ones that had lithium-6. And so it would imply that there is something directly influencing the only, of course, now from a physicist's point of view, that the only real difference in their properties is the quantum properties. You add a single neutron, that adds to the mass, which then goes into the Hamiltonian and the Schrödinger equation, which then you solve, and it gives you a wave function with a different frequency of vibration. Mm-hmm. Okay. Now the K value changes, and then the K value is the only thing that changes. The chemical properties are the same. The K value changes, which is the quantum property, and that somehow directly influences the rat's cognition, which is their inner mental state or inner spiritual state, as you would.
Yeah, so you're pointing out that most of us think about neurobiology and the brain as a chemical thing. So, if the lithium's bonding or binding to some neurons in our body, it would be because of chemical properties, the number of electrons that it has. And obviously that's not changing with the different isotopes. So the only thing that's changing is the wave function itself, the shape of the wave function and the frequency of vibration of that wave function. And somehow that's making a difference in their neuroanatomy or their physiology.
Now, what's kind of fascinating, both from just like a introspective, like just kind of observing this is kind of like it is a thought experiment, but it's also a real experiment because the experiment is on your own thoughts. But it's just kind of interesting to see how it fits together from like a metaphysical and philosophical. This is kind of where the philosophy and the science meet, because I'm kind of interested in fusing the two. Like I don't really have a preference for, well, originally my preference would be for the physics because I did the BA in physics. But right now I'm kind of in a place where like I see both of them as like very closely intertwined to the point where you could almost derive one from the other or vice versa. And what's interesting though is, okay, here's an example. I've tried this experiment with a whole bunch of people. What's your favorite favorite ice cream? Favorite isotope? Favorite ice cream?
I was going to say I don't really prefer one isotope over another. Favorite ice cream? How about Cherry Garcia, Ben and Jerry's?
Okay, and your second favorite ice cream?
Strawberry. Let's go with that. Chocolate chip.
So you have Cherry Garcia, mint chocolate chip?
Yeah.
All right, so you have Cherry Garcia. That's one of my favorites too. That and pistachio are my favorites. So you have, I've tried this experiment so many times. It's funny. I actually had I put this in a recent video earlier this year on vanilla and pistachio, and that wasn't a coincidence. That happens to be someone else's favorite ice creams that I tried this experiment on. Okay, so you go to the freezer, and there's Cherry Garcia, and there is mint chocolate chip, right? Mm-hmm. Open the freezer door. Now, because Cherry Garcia is your favorite, you might go for that first, right? But the catch is that you don't always do that, and it's just not, you'll sometimes waffle for a bit. Maybe I'd like to have the mint today,
Right.
Or maybe a little of both, or maybe we'll go back to the Cherry Garcia, et cetera. And now, if you were, remember the Terminator movies, and you could sometimes see the Terminator vision, and they had options to select. Mm-hmm. The first one I remember, there was Arnold Schwarzenegger was scanning through possible responses, and he ends up with "F you a-hole" to the guy who was outside asking if he had a dead cat in the room, right? Okay. Then later on, I think Terminator 3, they had Mrs. TX there, Kristanna Loken, scanning through possible alternate weapons, and then she selects one, and that's it, right? Uh-huh. If you notice, that's if you're thinking like a classical computer, okay? That's how you would be if you were the way kind of materialistic-minded models of the mind treat the mind, right?
Okay.
And you would just scan through, and you'd immediately compute this like in a fraction of a second, and you'd pick either Cherry Garcia or mint chocolate chip, just like that, right?
Right.
Now, and then you'd close the freezer door, and that would be the end of it, right? But in reality, that never happens like that, does it? You go to the freezer door, and you waffle, and you sometimes waffle for 4 or 5 seconds, maybe really long, and your wife gets mad at you because the freezer door is open. And
so you're getting at the decision-making process around ice cream is very much like a quantum decision, how quantum mechanics seems to decide between the options that are presented.
Yes. And it turns out that that's not just like a metaphor. You might think, okay, that's just a metaphor, Johanan, I mean, you might not think that, but someone in the audience might think that. But it turns out that's not actually the case. They've done very robust studies on this. The first time they noticed this was in stock market behavior. And they were recognizing, Ollie, that you could use the Schrödinger equation to predict stock market behavior, which is the very strange. One's economics, one's physics. And like, what does quantum mechanics possibly have to do with economics?
Well, the Schrödinger equation is essentially derived from wave dynamics. Any situation that involves the right relationship between derivatives, like rates of change, will obey a wave equation. And the Schrödinger equation is an approximation of quantum dynamics that basically Schrödinger said, hey, I bet the wave equation will work. Let me try it. And that's what he came up with. So
it does. Yeah. So
there's some reasons why they would have similarities, and quantum mechanics is not all that strange. If you, I mean, there's some very specific strange aspects.
What I was going to comment,
but most of it in general is a mathematical framework that's very
straightforward,
yeah.
Right? You have your Schrodinger equation, you put your energy values in, and out comes your wave function. And now, what's interesting though, if you think about the stock market, if you go to a trading floor, what really is that? It's just a whole bunch of individual people making individual choices to buy or sell. That's all it is, really. And of course, they interact with each other and so on. But fundamentally, it boils down to a bunch of people making individual choices. That's it. Buy or sell, spin up or spin down, etc.
Right.
And you think about that, and then you realize, then they thought, well, wait a minute, this is not just economics. This is something that's based on human decision making in general. And they expanded this, and they realized, okay, let's just forget the economics part of it. Let's look at human behavior in general. And they discovered then, quite astonishingly, was that the Schrodinger equation applies to human cognition. You can actually model. They have this whole thing called quantum cognition, which, whether or not the mind is actually quantum, what they're finding out is that it behaves as though it's quantum. And actually have an article, I think, in New Scientist, showing how your cognitive functions, it behaves as though there's a quantum field across your brain, and your thoughts are superposed states, and you choose one or the other.
That's a good lead-in to sort of give an overview of the research I've done since the last time we talked that I think your listeners will be interested in. I've been fascinated for years, since college, really, in the Fourier transform and wave analysis. You can break down any kind of waveform into its components by doing a Fourier transform. And it's a mathematical process that is really the basis of holograms. And in doing my research, I kept coming to descriptions of quantum mechanics that involve the Fourier transform. I mean, I didn't come to that. I even have a textbook that says, apparently, quantum mechanics seems to know about Fourier's work on integral transforms that was done 100 years earlier. And that's because, my sense is that's because quantum mechanics has as its foundation this process of the Fourier transform, which is the basis of holography. So in my work, I started to realize that the mathematical description of quantum field theory and quantum mechanics is identical to the mathematical description of light and diffraction. And diffraction is the mathematics of holograms. A hologram is like a photograph but it's not a photograph of an object, it's a photograph of an interference pattern. And when you shine light on the interference pattern just right, you get the appearance of an object in that area, but it kind of moves across the screen as you tilt it. So it's different from a photograph. A photograph is glued to the piece of paper that you're looking at, whereas a hologram will sort of float behind it or in front of it and move as you tilt it. And so I started to see that, well, if the mathematics of quantum mechanics is identical to the mathematics of diffraction and holograms, yes, like a rainbow, actually, I think is an example of rainbows have holographic aspects. They're not actually present out there in space. They move with you as you move. Like if you're driving along, you can see the hologram of the rainbow move with you.
You try and find it's just where you're trying to chase the end of the rainbow, and the rainbow just keeps moving with you.
Exactly. It looks like an object out there.
It's a very ethereal kind of thing.
And that's similar to how holograms work. And if that's the case, then there's some really interesting outcomes from that. First of all, just the idea that all of quantum mechanics is really just telling us that the world behaves like a hologram, in that the objects we experience, like my computer right here and my cup of coffee and all these things, these are the images in the hologram. But then we have to ask,
Schrodinger wave hologram.
Yeah. So what is the hologram itself? What is that piece of film?
Or you could actually say, maybe in a sense, that since it's the wave output, we don't actually see the wave. You could think of the hologram, the Schrodinger wave hologram, as the kind of computer behind the universe, and the output is the sense impressions we get that we identify with the quote unquote physical universe.
Yeah, and it's not like, it's important not to think of the computer computing the universe and the wave functions as somewhere like at the boundary of the universe. It's not somewhere else. It's this alternate space called frequency.
No, it's right there. Oh,
frequency domain.
That alternate space is Hilbert space, and that those computations are actually identical to the computations in your own mind. do I choose Cherry Garcia or mint chocolate
Right.
chip?
Right.
Accepting that, of course, it's not just your mind. There's a larger, what Jung, remember last time we talked about Carl Jung's collective unconscious?
Mm-hmm.
It's a big domain back there. That's your mind is just a very small subset, and you don't have access to the other parts. Or we'd have psi powers and basically be one big person rather than separate individual alters, like Bernardo Castro was pointing out. But there's this big domain, mental domain behind there. That's
so we have this. You use the term
essentially.
mental domain. That in music analysis, if you have a wave file of music, you want to understand its frequencies, the spectrum that makes up that music, like in an MP3 file, you convert it to the frequency domain, and you do that using the Fourier transform, just like you do for a hologram.
Mm-hmm.
And so the frequency domain is where the information exists. That is essentially, I mean, this is a little loose, but that is where the wave interference happens, and the Schrodinger equation describes the way that those waves exist. So the frequency domain is in this model. It's really important to understand the duality between the frequency domain and the physical domain. Our physical space and time is mirrored by a frequency domain of frequency and wavelength, but these are not physical waves. These are abstract information waves, and they are the basis of the physical world that we experience. And this is all new research that I'm doing. Yeah. So I can't claim that it's correct and that it's been verified, but it's work that's in the process of getting reviewed. So this let me tell you one really interesting outcome from this. You talked about macroscopic quantum objects like a car, and or even let's go smaller than that. I saw a TED talk about a guy who had an object that was like microns big. You could see it with your eyes.
You could see it was very small.
But he was claiming that it was in a superposition state. And that was like the attempt to take the microscopic particles, which can be in superposition, and create enough coherence and enough quietness around them so that they were able to stay in coherence and not get jostled by their environment. And he was able to get something really tiny, but that was still in superposition. But what we're doing there is something fundamentally, what I think is fundamentally, in some sense, misguided. We're trying to create macroscopic quantum superposition from microscopic quantum superposition. And the difficulty is obvious, which is that noise gets in the way and jostles these things, and they decohere according to the law of decoherence. Mm-hmm. That's going to fail. If you keep trying to do that, it's not what's actually going on, I don't think. If you think about it this way, in this model of the world as a interference pattern on a hologram, if you think about diffraction, which probably some of your listeners have, and most of them haven't. Diffraction is like when you shine light through a double slit and it bends into different bands of bright and dark. But also more generally speaking, if you look at the edge of an object, you might notice the light bends around it. You can see the pattern. If you look up close at it, you might see a pattern. And it's hard to see diffraction because it washes out most of the time, but it's the way that light bends around the edges of objects. Now, what's interesting about diffraction is that it doesn't diffract just one point at a time. It diffracts as a whole. So if I take this object and I perform a Fourier transform on it, I get a diffraction pattern of this whole object as a whole, not one atom at a time adding up to the other atoms at a time and creating a total image. But there's an interference pattern that would be created from this object as a whole, or a diffraction pattern. And so it brings in this concept that is present in holography of wholeness, that the object as a whole has properties which exist independent of the parts that make it up. And that's what a hologram is. It's a capture of the space that you can cut in half, and you can see the whole thing in each half. And so just to finish up that idea,
the information for the whole.
Yeah. The information is present at every
is located in simply the phase patterns. It's in the phase patterns of the waves themselves. So you just take the phase, you just pinpoint like what the phase information is at any one point, and of course it's going to generate the entire image because it's the whole image is just encoded in that.
That's exactly right, and it's a really deep mystery, and it points to the idea that maybe objects as a whole are have quantum properties, not made up of the electrons in themselves one at a time, but as a whole, each object is involved in the evolution of possibilities.
They have to. I mean, the whole notion of universal wave function entails that that's ultimately how they would break down.
It's a controversial idea. Let's just definitely say that.
It is controversial, but I don't see why it should be at this point. Like it's. I mean, it simply is. I mean, quantum mechanics applies. If you take quantum mechanics literally, then at some point the universe is a physical system. It should apply to the universe. So.
Yeah, and actually the
So
idea
I
that
feel.
quantum mechanics is universal is the way that physicists talk about it, and that's pretty well accepted idea. It's not off on the edge. So as you were saying earlier, some of these ideas have definitely gained more popularity over time that used to be more controversial. But it doesn't mean that we understand how to interpret them and make sense of them on a daily basis.
That's true. Now, as an aside, I had a kind of a cool thought. I had to throw this in here, even though it's not directly related, but it is directly related to this particular aspect of our discussion here. It's kind of a spin-off talk, a point. You've heard probably, you've heard of quantum teleportation, where they can transmit the information defining a microscopic, electron, or in some cases, several. I think they teleported like a complex molecule recently, or something like that. Mm-hmm. Now they're saying, though, of course, you wouldn't end up with Star Trek teleportation because, well, there's all these individual atoms in the human body, and you'd have to. I mean, you could do it, but the problem is it would take so long to scan in each one of these atoms. You have like trillions of cells, and each cell is comprised of trillions of, maybe even quadrillions of atoms, and so how do you do that, right? And so you would take, of course, if you have a perfect computer, right, even like not just like any a really good one, but like even a perfect computer, you'd have 1 bit per atom stored, right? Well, then you need a computer hard drive as big as the person himself. Right, this is completely impractical. So it's not going to, in reality, you're going to have a computer hard drive the size of Texas or something. It's just not going to work. Just to transmit a single, the USS Enterprise is not as big as Texas, which kind of sucks.
Right. So you're saying that there's a way that if you understand the object as a whole, not as a sum of its parts,
yes,
you have a very different problem to solve.
You can Fourier decompose. You can take a much larger object. I don't know how big you could scale this up, but it's the capacity for breaking it down at this point, when you recognize that, it becomes very immense. Right. And so you can then have an enormous amount of data compression, holographic data compression.
The analogy is between a BMP file and a JPEG file. In the old days, when they first came out with images, it was bitmaps where every pixel had a bit. Like you were saying, every pixel in my body would correspond to an atom. And that is just massively inefficient. And then JPEGs use the Fourier transform to convert it into the frequency space, throw out the unnecessary data, so you lose a little bit of resolution, and then convert it back into regular space, and you have the image.
Yeah, that's So if you could do that, though, if you could make a JPEG. Now, just as an aside, you might want to wait a little while between quantum teleportations.
Right.
I know this because I had the kind of like a hobby, as you know. I had a kind of a personal issue, shall we say, out in California. And while I was finishing my master's degree, I had this sort of hobby. I quit my job just to be able to focus on my master's degree, but to kind of distract myself from the pain, I put this hobby together and had these old lists of dinosaurs. And I have these, like, world's most comprehensive dinosaur chart, right? Which has literally everything on it.
Cool.
Like ever discovered.
That's cool.
And the thing with it is, though, is that when I say, ever discovered, is that changes every couple of weeks. They find on average 3 new dinosaurs a week, so a month rather. I got to update it on average. I have to update it constantly. And I discovered that if I put stuff in JPEG, it will actually, and do it too many times, it starts to significantly degrade the quality of the image. And it's like, so I do it in bitmap on purpose because that way it keeps it.
Because every time you do it, it's throwing out some information. And I can't imagine if you decompose yourself into your frequency spectrum, threw out some of the high frequency information that you couldn't see, you'd still be losing some over time. I'm not sure exactly what you would lose, but it would be part of you, and that's probably not a good thing.
Yeah. So what I'm thinking is, in that case, you might want to teleport. Like, you want to have a limit on how many times you teleport. If this were to become practical technology, a limit to how many times you teleport a week, kind of thing. Well, you want to have some time for your body to adjust. And
there's a lot of folks who look at technology from that perspective and are very excited about the technology of the future. And I keep bringing this technology and these ideas back to the technology we have not mastered yet that's right in front of us, which is our own personal inner state, our ability to navigate relationships, navigate interactions with each other. And my work ultimately comes back to choices, as we talked about earlier. The choices of our consciousness affect what we experience. And that's why I wrote a book called Living in Flow, because when we start to understand the way our choices are bringing about synchronicities in our lives, the way that the cosmos is essentially responsive to us, then we start to, for me, it's like a level of responsibility that I start to feel for my own experiences, realizing that the choices I make really make a difference. They really have an impact. And all sorts of little choices throughout my day change the direction of the course of my life. So I think we can make a lot of progress even before we invent teleporters and, uploading our brain to, make ourselves invincible or whatever that technology is. Making life more worth living by making choices in our lives that are better and that don't alienate other people and help us connect on this planet,
Yep. Now, I wanted to go back to a topic that we talked about very briefly right at the beginning. We got to Copenhagen, but the thing with it is the other branch of interpretations. I mean, there's a lot of various interpretations, but there are two of them. A lot of them are they don't seem to work too well. There is, however, one that does have some validity as well, it seems, or at least some, there's a lot of traction behind it, and it does ground itself in high real sickness. It grounds itself in, in actual aspects of the Schrödinger equation.
Okay.
What?
I was saying high to real sickness.
Namely, superposition. Yep. Oh, yeah. So MWI, right? Now, this is kind of preferred by materialists because you don't need consciousness per se. At least that's what it seems to be. You can just say that, it's all real. It's just that there's all these multiple universes, right?
Many worlds, yeah.
Now, as it turns out, that's not exactly entirely true, because it turns out that it has something called the preferred basis problem, as to why should something either be a wave-like or particle-like at any given time, and what defines how it should be. And so they've solved this recently, but the problem is in order to solve it, they have to use emergent spacetime, which, as you know, emergent spacetime is very anti-materialistic because it takes away the entire backdrop that space exists in. It's you can't. There's Democritus's atoms in the void, and you can't have Democritus if you don't have the void, and emergent spacetime gets rid of the void. So now that's the kind of the interesting thought there. But now the issue with this is that's not explicitly, say, idealistic or tying consciousness in. But now what I thought was interesting is your work. It obviously does deal with these multiple branches, right?
Mm-hmm.
And I wouldn't say it necessarily tails MWI, but it does seem to lend a level of credence to it. It does seem to that would fit with MWI in some sense. And I've had some thoughts on how to tie them together.
It's absolutely. I use many worlds interpretation as a guiding principle a lot. We don't want to jump to the many worlds interpretation in thinking that there are many physical worlds. Like a lot of people get all in their heads science fiction-y about it and say, "Oh, there's a different version of me that made a different decision yesterday and is on a different parallel reality." The many worlds interpretation, I think, is talking about the information about the world, but the relational model of quantum mechanics, which is related to the many worlds interpretation, says that the quantum collapse is a relational process. In other words, I experience the world from my point of view, and what choices collapse into place a certain way for me, and that might not. And they don't collapse for you just because they collapse for me. And it's only when you and I meet that whatever we share in common is collapsed for both of us. So there's this idea that, and this gets back to the holographic idea that we're living in a virtual world. And again, we don't want to go too far down that without analyzing what I mean by that. But in a very real sense, the physical world we live in is presenting itself to us as a virtual world that we can interact with. But it's virtual in the sense that it doesn't persist when we're not looking at it. So when I look away from something, it starts evolving into many possibilities. It doesn't have a physical, definite reality without my observation. But that's just from my perspective. So it's like a virtual world created for each of us to interact with. And that means that the many worlds theory doesn't say that there's a gazillion objective universes out there. It says that each of us is experiencing our perspective on that tree and we're at a particular point, and then we interact with each other on that tree, and we have shared realities. But we have to stick to what we ourselves observe and not try and talk about it as if there's some objective, definite thing going on out there around us.
Right. Now, I had a thought, and this is where, because I noticed, I mean, for example, idealism out of combining emergent space-time with Tononi's IT, right? And that's it's all science there, going kind of an empirical approach, but you then ended up with this, yes, integrated information theory. This is very philosophic conclusion, which is idealism. And I noticed other places where you can, for example, recently I connected entanglement with, I mean, actually Hoffman did this, and I applied it in one of my recent videos, connecting entanglement with the phenomenon of binding in consciousness studies. You know, why you experience a whole experience rather than dissonance, right? Now, what I was thinking is, it comes from a completely philosophic angle, but then it had a striking resemblance to the superposition principle and the notion of the superposition principle being in the wave function when you take like the philosophy model and translate it over to the physics model. And just kind of bear with me when I kind of explain this. So let's go. We can derive idealism in a very philosophic sense from one of the many arguments, maybe Berkeley's arguments, maybe some of my own, like, introspective argument, mind is immaterial, from this basic observation, and then dualism is incoherent because of the interaction problem, and you got idealism. Now, idealism, you have a physical world, and then you have beneath the physical world is this layer of ideas that generate it. Remember, that's the information generating the physical world, right? Now, however, what's curious about this is that means that a universe is identical to an idea, essentially. The mind of whoever up top, what we're seeing as a physical world is actually a idea, correct? Now, what's interesting, though, is then when you take this in the kind of a Tegmarkian direction, Max Tegmark with his whole mathematical universe hypothesis, if you think of ideas, right, how many ideas are there? It's like asking how many mathematical equations are there.
Sure.
It's unlimited, right? They all exist. All possible ideas exist, right?
Right.
And so Tegmark then ties this into this mathematical universe hypothesis where he says we are essentially one of these mathematical constructs. All valid mathematical constructs exist in their own right. And so what we see, physical reality as we think of it, is simply the experience of being inside of one of these mathematical constructs, yet they're all real. And so therefore, there are other realities that it may not even be, just other choices of us. They may be completely bizarre things described by totally new laws of physics that happen to be, or there may be some connection to, I have a suspicion that the laws of physics are a little more necessary than we might think. So there might be some limit on this, but basically, any possible mathematical function is its own universe, right?
Right. Okay.
Now, what I was thinking though, is let's take that on board for a second. And so you have Max Tegmark's, these whole bunch of these different mathematical functions or ideas, as it were. Maybe you extend it to like just Platonic ideas, etc. All possible ideas exist. And then where are they located with respect to you and your physical reality? They're behind it, right? They're in that God's mind space, you might call it. The Neoplatonists called the pleroma, right? Of all these different Platonic forms or objects back there. Mm-hmm. And that's what is behind the universe. But now let's translate it back into a physics model. Okay, so you got the physical world, that's what's rendered, and what's behind it? Well, that's Hilbert space, aka the quantum wave function. Now, then you kind of tie the two together. You notice something very interesting popping out of this is that in the physics model, it's the wave function, but then you translate it over to the philosophy model, and what it says is, well, it's all of these many different worlds of, basically Tegmark's mathematical universe, or Plato's world of forms, basically, of all possible worlds existing, and each one of them internally is as real as our own. And that's the philosophy, but then you translate back to physics again, that's the wave function.
Right.
It looks kind of interesting. It looks pretty familiar, doesn't it?
Yeah, I like that. I'm going to have to have this be the last comment, and then I'm going to have to drop off and lead another session for a course that I'm teaching. And but I think that gets back to the relationality idea that I look at Hilbert space and the frequency domain are related to each other, and it's I don't know that I could even describe accurately hear what that relationship is, or I'd have to do a little more reminding myself and studying. But they're related. This idea of the frequency domain that supports the holographic worldview and Hilbert space that you're referring to in quantum mechanics, that in which the wave function exists. So I think that there's a real connection between. I think that we can derive quantum mechanics from the mathematics of diffraction and relate these two theories. And there's some benefits to that, diffraction and optics are something that the study of light is something that we understand pretty well from a practical point of view. And it illuminates some of our understanding, I think, of quantum mechanics. And this is part of a paper that I'm working to publish right now. And one of the things that this approach gives us, I think, is it requires relationality. It requires that the collapse of the wave function is a relative process. So when I make a measurement of my electron in a lab, I get a result. But this is called the Wigner's friend paradox. If another person comes along, my friend, and it isn't in the room when I make the measurement, the question is the thing I'm measuring still in a superposition, or did the fact that I measured it make it collapse? And a lot of folks who are very materialistic would come in and say, well, it already collapsed because the first person measured it, so it has to be in a definite state. But what we've found and there's an experiment that was done last year that indicates experimentally that this is the case, that both the thing I'm measuring and me are in a superposition, and which forces us into understanding relationality in a different way and deciding that quantum mechanics is a relative process of measurement.
People who deny that this is relational, it just seems so stupid to me. It literally is just like they're not taking quantum mechanics. They take it and then they would say like, "Oh, but then we're going to stop applying it at this one point." And like,
yeah, I think that's true, and I think we're all subject to our preconceptions about what the physical world is like and what life is like, and the world looks a certain way to us. So when we have mathematical theories that seem to contradict that, it is hard to adjust, and it's not always wise to adjust. Sometimes our observations are good. So I have I've
noticed that until very recently, and I'm hoping maybe we, not us two in particular, but like we as a community have kind of pushed this, is that until very recently, that whole von Neumann and Wigner's friend were very directly connected to, just tied directly to physics, right? It should follow from the physics, and yet only like 5% of physicists, 6% of physicists were taking it seriously until very recently.
Well, I even say I've written in my paper before, this approach implies that
now it's 22%.
That collapse is a relational process, and a lot of physicists will say, "I don't know what you mean by relational," and the fact that I have to define that, it seems to imply that I haven't even given it any thought, which surprises me because it's been published. These ideas have been published for decades.
That's very frustrating.
So I think that there's
I think we just, I've noticed for a long time they just call it pseudoscience until you push it out and you like say this is what the physics says.
Well, and in the 60s and 70s,
did an experiment.
When they came up with Bell's theorem, when Bell came up with his work in the 60s and showed that local realism can be experimentally tested and properties may not actually exist until we make a measurement. At first it was seen, maybe as pseudoscience or as very like not accepted, let's just say. And then gradually more experiments were done, like Alan Aspect's experiments in the 80s, and showed like, wow, this is really true. And then recently there was an experiment that was done using light from opposite corners of the sky, some hundreds of light years apart from each other. So, and they showed that these two light particles were able to obey the same quantum mechanical disruption of when one was measured versus the other that we would expect from entangled particles locally, in our lab, showing that quantum mechanics applies to things that are vastly separated by vast distances, not just it's not just a quirk of certain experiments we can set up, but it's definitely a universal process that there are really no remaining loopholes to. Yeah,
that has a very when you get to that level, it feels like the world is it really kind of settles in just how real it is, because it almost feels very artificial in a way at that point. It's like living in a fictional universe, and there are what's the word? Retcons being stuck into place at the last minute,
Right. Okay.
Retcon. You've retconned the activities of an entire solar system hundreds of light years years away into existence right here at this location in space, right where you are at this point in time.
Yeah, these are tricky issues, and
it feels very
Real Cygnus brings up the
plastic. It's kind of spooky.
the VR information more. So I think next time we got to get back on here and talk more about virtual reality and what that really looks like.
Yeah.
From a, can we consider this world as, in some sense, as virtual? And I'd love to talk more about that in the future. So thanks for having me on.
Yeah. Yeah, definitely. Should I end broadcast?
Sure. Thanks for joining, everybody. It's been great to see you. And sorry I have to go, but I look forward to coming back and talking with you more about this. It's great to see you.
All right. Sure. Definitely. It's good to have you again, Sky.
All right. Take care.
Yep. End broadcast. Is it ended? Hold on. I don't know if it's responding. Oh, here we go. End broadcast, right? My interface is a little finicky.